So we're looking at page 63. The question here is claim that apples are the most delicious fruit on the planet. Test this claim. Let us determine if the majority of the population responds apples when asked what they think the most delicious fruit is. So a sample of 4,500 people are randomly selected and polled. It is determined that 2,475 people chose apples as the most delicious fruit. Using a 0.05 significance level, test the claim that the majority of the population finds apples to be the most delicious fruit. All right, so the first thing we want to do is establish what our null and alternative hypotheses are going to be. All right, so the null hypothesis would be what this population proportion, because we are talking about percentages here, would be equal to under normal circumstances. So the key word here is majority. A majority would be a proportion that is greater than 0.5, greater than half of the population. All right. Now, since a null hypothesis always involves an equal sign, this must be an alternative hypothesis. All right. The null and alternative hypotheses always go hand in hand in that they have the same structure, except the null always has an equal sign. So whatever the ingredients are of the alternative hypothesis, you're going to have the same ingredients for the null, except with an equal sign. All right. Now the calculator test, whenever we're dealing with a population proportion, so this is one population proportion, the calculator test is going to be a z-test. All right. And that's essentially because it's a z distribution. So it's really not so much a matter of the kind of test as it is as much of the kind of distribution that we're going to be using. All right. After that, we want to make a determination of what the p-value is and then compare that to the alpha. They told us the alpha was 0.05. Significance level is your alpha. The p-value is going to come from your sample statistics. All right. So what they told us here, all right, so they told us that there were 2,475 people who chose apples as the most delicious fruit. All right. So the sample size is 4,500. The number of successes, which is why I slipped up a second ago, is going to be 2,475. So that 4,500, that's your n value. 2,475, that's x. All right. So what we can get from this is a few things, but most importantly, we can get a test statistic. The test statistic comes from the formula z is equal to p hat minus p over the square root. That looks fun. Of PQ over N. Okay, so that P hat, that's a weird one. That P hat is the ratio of X to N. All right, so P hat, so where P hat is equal to X divided by N. All right, so what we're going to do is compute this test statistic and use that to determine our p-value. All right, so what we want to do is determine the area in the standard normal curve that's to the right of the test statistic. That's going to be our p-value. All right, the reason why it's to the right is because the alternative hypothesis has a greater than symbol. All right, so if I just draw a quick sketch, and I'll just kind of chuck it in over here. Just move this over. resize a little bit. And zoom it in. I got all that negative space at the bottom. I wish I spaced this out a little bit better. I'll take that as a typo. All right, so what we're looking for is this area. If we have the test statistic, TS for test statistic, for whatever that Z value is, whatever this area is, that's our p-value. All right. So that's where Desmos comes into play. All right. So what we're going to do is first compute the test statistic itself, and then find the area to the right. All right. So in computing the test statistic, it's going to be Z equals the X value divided by the N value, 2475 over 4,500, minus that p-value. We always go with the assumed p-value. And be careful. I mean, I've already said it a couple of times, so I know it could be confusing. P-value is a term. The value of P is what I'm referring to here. So this P, this population proportion, is the assumed one from the null hypothesis. All right, so we're going to say minus 0.5. And that part I know is definitely confusing. It's just in probability, like there's so many things conceptually that start with the letter P, you know, proportions, percentages, probabilities, and then probability of what? You know, and so everything could be abbreviated in that context, could be abbreviated with the letter P, and so there's bound to be some confusion. All right, so it's unfortunate, but that's the nature of the beast. All right, so the P that's referenced in this Z statistic formula is the P that we used in the null hypothesis. All right, so then this is going to be over the square root of PQ. Q is 1 minus P, so it's also 1. It's also 1/2 or 0.5 over the N value, which is 4,500. All right. So if you want, let me make this a lighter color. You might want to make a note that that Q is equal to same as 1 minus P. All right, so this is what we're going to crunch in Desmos. So we would, you know, we don't have to put the Z in if we don't want, but I want. So Z equals fraction, another fraction, 2475 over 4,500 minus 0.5 over the square root of 0.5 times 0.5 over 4,500. All right, so we're getting approximately 6.708. All right, so all I need to figure out in order to determine my p-value is the area in the standard normal curve to the right of that number. All right, so what I would do is I would now select function, distribution, normal distribution, 0, 1. Now, check off the box that says find cumulative probability. If we bring it in, you know, kind of get a good looking zoom there. It doesn't have to be perfect, but you want something that looks sort of like a standard normal. So, I mean, I could change my Y scale here. So I'm going to make my Y-axis go to, like, let's say 1. And then, well, on the low end, I also want to change that. So let's make that like 0. Let's make that 1. I don't need to go negative 10 to 10. Let's do like negative 5 to 5. At least kind of look something roughly normal. Now this is way more shaded in than we need it to be. I only want the the right tail of it shaded in. So let's modify this. Now, I wanted to start the shading at the z value that we determined to be equal to 6.708. So for my minimum value, I'm just going to type in z, or 6.708. Now, I did a ballpark estimate when I plotted this, this rough sketch here. This doesn't look anything like that. But it actually kind of makes sense, because if you go based off of the standard normal curve and its scale factors of 1 standard deviation along the horizontal axis, it kind of makes sense that this would really be somewhere out over here. So this area is very much an overestimate, but we didn't know that going in. But now we can make a little bit of an adjustment as we kind of think about it further. All right. So with that in mind, I now know that I'm looking at this teensy tiny little area that ends up being about 9.852 times 10 to the negative 12th power. All right. That's our p-value. All right. So we're talking, like I said, 9.852 times 10 to the negative 12th power. All right, that's infinitesimal. All right, that's teensy tiny. All right, so what that tells me, because based off of the relationship between the p-value and the alpha value, we can draw the conclusion of whether or not we're keeping the null hypothesis. If the p-value is less than the alpha, I'll just jot that down here. If p-value is less than alpha, then reject the null hypothesis. All right. So if the p-value is less than the alpha, reject the null hypothesis. Well, this p-value is teensy tiny. This one's small, but it's not this small. This one's like practically 0. It's definitely less than that value. All right. So in this case, we were looking at a true sentence here. The p-value is less than the alpha value, so we will reject the null hypothesis. All right, so that null hypothesis is bad. The alternative must be the winner. And so the first sentence is always going to address the null hypothesis. So addresses, regardless of what the question's asking you, the first sentence always addresses the null hypothesis. So when it says there is blank, insufficient or sufficient evidence to reject the claim that, we would state the null hypothesis in words here. P equals 0.5. Well, what does that mean? That means that the population proportion of people who chose apples is 0.5. All right. Population proportion of people who chose apples is 0.5. That's, in words, what p equals 0.5 means. At the blank significance level that was given, they told us it was 0.05, so I just popped that in there. Therefore, the claim that, all right, the claim that what? Well, the claim that they're asking us, that the majority of the population thinks apples is the most delicious fruit. So the first sentence addresses the null hypothesis. The second sentence addresses the question, which most often is the alternative hypothesis, but sometimes it's a variation of the alternative hypothesis or the question, or both. All right. So therefore, the claim that the majority of the population now, it's a little verbose to say finds apples to be the most delicious fruit. We'll just say chose apples. Is what? True or false? Well, we got to make two decisions here. Are we talking about sufficient evidence or insufficient evidence? Well, it's a question of whether or not we're rejecting the null. This first sentence is the null hypothesis. Yes, we are rejecting the null. That means that there was sufficient evidence to make that rejection. All right. So if we are rejecting the null, we're saying the null is bad, that means the alternative is good, good as in true, we're making the claim that this is a true sentence. The majority of the population chose apples is true.